Hey everyone, and welcome to this explainer, brought to you by Forge College. So in our previous module, we were doing some incredibly heavy lifting, right? We were extracting massive amounts of raw data to build out the core components for the Solana Cloud capstone. It was messy, it was deeply technical, and honestly, it was brilliant. But today, we're pivoting back to our Ethereum fundamentals track. Specifically, we're diving into gas mechanics and optimization. Today's explainer is all about taking that raw, chaotic data you've gathered and transforming it into an elegant, highly actionable engineer's blueprint. We're talking about integrating optimizations and formulating rock-solid recommendations. Let's get into it.
Okay, let's dive into this. We've got a highly structured agenda today to build out our engineering schematic. We're going to start by moving from raw data to action. Then we'll build our core artifact, the comparison table. After that, we'll quantify our savings and confidence, map out evidence and prerequisites, and then do some rigorous spot checking on our recommendations. Finally, we'll wrap it all up and finalize your capstone blueprint.
All right, Section 1, from raw data to action. Let's get moving.
So, we are officially transitioning our narrative out of the messy, chaotic laboratory of your analysis notebooks and into the clean, well-lit, highly structured room of actionable blueprints. Because let's be honest here, handing a stakeholder your raw Jupyter notebook outputs, raw datasets, and just a bunch of floating p-values, yeah, that's an absolute nightmare. It is literally the quickest way to make a client's eyes glaze over. Numbers without a structured, compelling narrative are basically just noise. So our job right now is to synthesize those results into a neat, actionable blueprint featuring clear, quantified, and completely traceable optimization recommendations.
To actually pull this off, we're going to use a strict 4-step assembly line process. It's like a machine. Step 1. We scan your per-operation breakdowns for candidate optimizations. Step 2. We compute the estimated gas savings for every single candidate. Step 3. We assign rock-solid confidence levels. And finally, Step 4. We map those claims directly back to the evidence. This is exactly how we turn raw materials into a verified schematic. Moving right along to Section 2, building the comparison table. This is the absolute star of the show.
This brings us to the artifact that ties this entire capstone together. Strictly defined, the comparison table is a single, highly structured CSV or Markdown artifact. It organizes every single recommended optimization you've got. It lists the estimated savings, a confidence rating, the required prerequisites, and your exact evidence pointers. Think of this as the core schematic you're drafting to meet your capstone success criteria. It's not just a table, it's the ultimate source of truth for your project.
Now, what's really interesting about this is how we start building it out. We start incredibly simply. We begin with just 2 columns. First, the optimization ID, so let's call it opt-001. And second, a brief, precise description of its mechanism. So, in this case, pack 2 status flags into a single uint8 slot. See? We are just establishing the what right now, before we even touch the how much. Which brings us to Section 3, quantifying savings and confidence. It's time to add the crucial metrics.
Okay, once we know what the optimization actually is, we have to move the process forward by adding the exact metrics stakeholders actually care about, exactly how much gas we save, and exactly how sure we are about that number. Let's look at a very specific example here. 210 gas. Now you might be wondering, where does this number even come from? Well, it's just simple math derived from your previous analysis. You take the baseline gas mean and subtract the optimized gas mean. That's it. So, if your baseline was using 2 storage slots and your optimized version packs them together, the delta there is your estimated gas savings.
But here's the thing. A number means absolutely nothing without confidence. Your confidence level is a rating, high, medium, or low. And it's derived directly from your statistical significance, sample size, and sample heterogeneity from your lesson 3 tests. So for example, if your p-value is less than 0.01 and your sample size is over 100, boom, that's high confidence. But if your sample is tiny or the tests are inconclusive, you're looking at a low confidence rating. And let me tell you, pitching an unverified, low-confidence recommendation to a stakeholder as a sure thing, yeah, that is a fantastic way to lose a client's trust entirely. Don't do it.
So we take those metrics and add them to our schematic. Our table is growing. It now has 4 columns: the ID, the description, our estimated savings of 210 gas, and our high confidence rating. Oh, and a quick pro tip for you here. If you ever look at this table and see negative savings in that column, you probably made the classic rookie error of transposing your baseline and optimized columns. Actually, it happens all the time, so always double-check your math. All right, Section 4, Mapping Evidence and Prerequisites. It is time to bring the receipts. Now we shift our focus to the concept of proving our work. Because look, anyone can just punch numbers into a spreadsheet, right? But a real engineer proves that their math isn't just pure guesswork. So the crucial point here is the evidence pointer. An evidence pointer is a concise reference to the exact Jupyter Notebook cell ID or the aggregation CSV row that completely supports your guess estimate. It is the irrefutable proof you bring to a skeptical client. If they question your 210 gas savings, you don't get defensive or argue, you just point them straight to Notebook cell 58. Done.
Alongside evidence, we absolutely need prerequisites. These are the minimal technical requirements, code changes, and specific testing actions needed to implement your optimization safely. Stakeholders absolutely must know what might break before they implement your brilliant idea. Do they need to upgrade a contract from V1 to V2? Do they need to run full regression tests? Whatever it is, put it in the blueprint so there are zero surprises.
And this brilliantly illustrates our final, fully assembled comparison table row. We've got the whole shebang: the ID, the description, the savings, the confidence, the prerequisites, and the exact evidence pointer. This right here, this is the gold standard. It is no longer just a messy spreadsheet. It's a fully traceable, highly actionable engineering artifact.
Moving into Section 5, spot checking your recommendations. The old saying goes, trust but verify.
We aren't quite done yet. Before we stamp this blueprint as finalized, we have to spot check our work. Treat this as your final, rigorous clipboard checklist. To pass, every single optimization must be traceable. The quantified savings must be mathematically consistent. The confidence levels absolutely must be statistically justified, and finally, the prerequisites must be actionable and specific. If a row fails literally any of these checks, it goes right back to the lab. This spot checking is a highly specific process. Step 1, you literally follow the evidence pointer you wrote down. Step 2, you rerun that specific notebook cell or check that aggregation row. And step 3, you confirm that the resulting delta perfectly matches the exact value you put in the table. It's a closed loop. And here is a fantastic golden rule of thumb for you, the number 3. You must perform at least 3 independent row checks before you can confidently stamp the overall blueprint as validated. So choose 3 different optimizations, completely at random. Run that 3-step spot check process we just talked about, and if they all match perfectly, your comparison table is officially ready for the real world. And finally, Section 6, finalizing your capstone blueprint. We've reached the ultimate phase. That brings us to wrapping up your capstone blueprint and preparing for the next phase of this track. I really want you to remember this next phrase because it's honestly the core philosophy of this entire Ethereum fundamentals module. An analysis without evidence mapping is just a guess. Read that again. We are engineers, we're not guessers. The precise mapping of raw data to a structured narrative is exactly what makes your work professional, credible, and immediately valuable.
Let's zoom out for a second and see how this builds across the whole track. In Lesson 2, we normalized the data. Then in Lesson 3, we performed the heavy statistical analysis. Currently, we've synthesized all of that into our pristine comparison table. And next lesson, we take this very table and embed it directly into the final gas analysis report assembly. It's just a really beautiful logical progression.
So I'll leave you with this final, provocative question. If a stakeholder challenges your most ambitious, aggressive gas optimization, exactly which notebook cell will you show them to prove it works? If you've built your comparison table correctly today, you already know the exact answer. Thank you so much for joining me on this explainer made by Forge College. Be sure to visit forge.college to dive deeper into the subject and discover a wealth of other fascinating Web3 related topics. Keep building, keep optimizing, and I'll see you in the next one.